So yeah, this is Matt. He's going to talk about wireless fundamentals, and also after that he has a short announcement about Ubiquiti, which is quite exciting. Yeah, have fun.
Hello, everyone. Is it okay? I don't speak German, so I hope that you can understand my English. Uh, we've worked with Momo for a while, maybe half a year, 1.5 years. But about half a year ago, he emailed us with some security vulnerabilities in our products. So we became in close contact with him. He helped us patch some of our software before it got taken advantage of and exploited by malicious users. So since then, we've been trying to get more in touch with the security community, and I'll have some more announcements about that at the end of the presentation. But he invited us to come to this show and kind of see what you guys do here. We donated a couple of pieces of equipment, and he asked if we could give a short presentation, and it took me a while to figure out what we would do. But today I thought I would talk more about wireless fundamentals and RF theory, just how wireless works. We all use wireless on a day-to-day basis, but a lot of us don't know exactly how it works, why it works, how to troubleshoot, and things like that. So just a quick show of hands. How many of you do any kind of ISP work? Are most of you IT guys? You do indoor wireless? Anybody do outdoor wireless? Okay, cool. Some of you guys are good with wireless. So that's what we traditionally do at Ubiquiti. We first started out in 2005 doing embedded mini PCI radio cards that you can take, hook up your own antenna, your own software, build your own product from scratch using our embedded radio cards. It was very popular in the wireless ISP industry. And then we started getting more into complete products. So now, if you see our products outside, like the air fiber that he discussed, we developed the software, we developed the hardware, the radio, the antenna, everything we build in-house, and we ship as a complete unit. So that's what the majority of our customers are all outdoor wireless ISPs. So that's what I'll be discussing today. I'll try to keep it a little more generic, so it's more about general RF and radio frequency theory. And I'd like to keep it informal. So if you guys have any questions, feel free to raise your hand in the middle, because we'll be talking about a few different topics. So if there's anything that you have a question about, just raise your hand and we can stop and discuss. So the first thing, frequency and propagation. You all know about RF, wireless, the access points that you go to the store and buy, like the access point we're using here. It's dual band. It's 2.4 and 5 gigahertz. So wireless products run on different frequencies. In the outdoor wireless industry, we have multiple frequencies we can use. These headsets, it looks like they're running on 800 megahertz. In the US, we have 900 megahertz. We also have 2.4 gigahertz, 5 gigahertz, which is pretty much unlicensed around the world. These all have different pros and cons. So the main difference between the frequency is propagation. The lower the frequency, the better it is at propagating through objects. So this 800 megahertz or 900 megahertz will do a lot better going through walls and other obstructions than higher frequencies. It's the same thing with the indoor access points you can buy at the store. 2.4 gigahertz, if you have it installed in your house, will do a better job of reaching a farther distance than 5 gigahertz, because the 5 gigahertz may be blocked by the walls. So that's one of the first fundamentals about radio theory. And that's all because, I don't know if you can see the slide, it's kind of dark, but the lower the frequency, the larger the wavelength. And that has a lot to do with a few different things we'll be talking about. By the way, I really like this drink. Yesterday was my first day having this, and I think I'm addicted. So I think I'll have some in my bag on the way home. This slide goes over some of the things I just mentioned. Just some different options that you have for outdoor wireless. There are a lot more options than this, and there are many countries around the world, and everybody has their own rules. So we're an equipment manufacturer. It's very difficult for us to keep up with all of the rules Europe they have their own rules in Europe, and then even within Europe, Germany, Switzerland, Spain, they all have their own rules. U.S. has their own rules. Asian countries have their own rules. But these are some common examples: 900 megahertz, 2.4, 5 gigahertz. Like Momo mentioned, they installed the 24 gigahertz link outside. So 24 gigahertz is another option you can use. I don't know the specific rules in Germany, but it's unlicensed most places around the world. Question?
Yeah, does unlicensed mean that you are not allowed to use it, or that you're not sure that the frequency is not used by anyone else?
Okay, so the question is about unlicensed. What exactly does that mean? Good question. So in wireless, outdoor wireless specifically, there are two different types of wireless. There's the licensed kind, where you go to the government and you say, I'm going to put a radio here, and this is what frequency I'll be operating on. I'll pay you, some money, and you're the only person that can use it. It's yours. You licensed it. If anybody else comes and tries to use that frequency, you say, I have this license. You can't use this. On the other side, unlicensed, you can take a radio, and without worrying about the government, you just put the radio up. No problem. So 24 gigahertz is unlicensed. They didn't have to deal with the government. They installed the link in one day, and it's passing terabytes of data. If you want, you can take the link down, go put it somewhere else. It's unlicensed, so it's not a big deal. So we deal mostly with unlicensed radios, just because it's easier to install. Okay? So next section, I was going to talk about dB, decibels. That's how we measure power in wireless technology. Have you guys ever seen the dBm power ratings? Okay, cool. A lot of people, there's a lot of misconception about dB and dBm, dBi when people first start learning about wireless technologies. And it's actually pretty simple. The decibel scale is a logarithmic way to show power levels because with the power levels of wireless radios, you can start very, very small, like 0.000001, and go up to positive numbers, 5, 10, 1 million. So in order to show that in a way that's easy to read, easy to write, easy to do math on, we use logarithms and convert those to a decibel value. Decibel values are relative ways to show large values. So in specific, with radio, we measure in dBm, decibel, which is relative to the milliwatt. Milliwatt is the amount of power that a radio outputs. So I don't know if it's easy to see. 1 milliwatt is equal to 0 dBm, but you can go up to 1,000 milliwatt, or 1 watt is 30 dBm. So it's just an easy way to keep track of large amounts of value. And if you ever have questions, you can go, there are calculators online, so you can convert from milliwatt to decibel. It's pretty useful. One thing that I wanted to talk about today, it's an interesting topic, not many people discuss it, but radio sensitivity with different channel bandwidths. So with home or office type access points, you usually don't have the chance to modify the channel bandwidth. And the channel bandwidth is the amount of spectrum the radio uses. So if you can see, some common examples are 5 megahertz of spectrum, 10 megahertz of spectrum, 20 or 40 megahertz of spectrum. And all of our outdoor radios and other vendors' outdoor radios, you can select different channel sizes. And there are benefits, there are pros and cons to using smaller channels and larger channels. So with the smaller channel bandwidth, the radio sensitivity increases. So you can have a signal level down in a very, very, very low signal level. In this example, we show 5 megahertz works down to negative 107 decibels, dBm. That's because the smaller the channel bandwidth, the better it works in noise and low power environments. So this is one thing with cell phone carriers. They use very small bandwidths. And if you ever look at your cell phone and see what kind of signal level you have from the cell phone carrier, you can have very low signal and still have good service. But with larger channel bandwidths, by default, The access points you use at home, 2.4, they use 20 megahertz of bandwidth. And those require a lot higher sensitivity to work, or a lot higher signal level. In contrast, if you use too low of a channel bandwidth, the performance drops. You don't have as much spectrum to use. So it's actually Shannon's law says the more channel bandwidth you have available, the more throughput or performance that you have. And it's pretty common sense. You have more channel frequency to use, you can send more things over that frequency. And then the next thing, how does a radio actually take that frequency and turn it into anything useful? This is one thing, for a long time I worked with wireless, and I knew that you have these two radios, they talk to each other, and it creates a nice layer 2 bridge. You can pass Ethernet traffic over it, it's easy. But how does that work? So the way that wireless works is, as you saw from the first slide, radio works in waves, right? Radio waves. And based on these waves, the radio can take these waves in and translate them into binary digital data. And the way this works is by two different methods. One is by changing the amplitude. So the radio wave travels like this. You can change the amplitude, which is basically the height. I wish I had a whiteboard or something. But you can change the height of the wave, and the receiving radio can see that and measure the height and say, okay, this amplitude translates to this binary data. You can also change the phase. The phase shifts the radio wave in before or after. So you can change the amplitude and the phase. Go ahead.
Before or after what reference?
Just where it is. I'm sorry, I wish I had a whiteboard or a better drawing. Hold on, let me see.
Can you repeat the question, please?
He asked, change the phase in reference to what? So if the radio wave has two different ways. Again, amplitude and phase. Phase basically just shifts the wave. So the receiving radio can measure if it's in phase or out of phase, and then translate those two items into a modulation. And this is one example. Actually, let me start with BPSK. So BPSK is the most simple modulation. It's only two options. It's binary phase shift key. So with this, if the phase is shifted just a little bit, it's very easy to tell because there are two options. In this example, there is no amplitude changing. With this, it's very reliable. If the phase shifts just a little bit, you can tell whether it's the 0 or the 1. It's very easy to decode. It's very reliable. If there's any kind of error, it's very easy to correct. But there's not much data that can be passed with this, with only two items. If we go up to a more complex modulation, 64 QAM, you can see there's a lot of data, but it may be harder to decode. I have one example here. So as you can see on the left, as the phase and the amplitude are adjusted, the receiving radio takes this and translates it. This is kind of a visual representation of what the radio sees on the left side. The dot doesn't always appear exactly in the left spot where the 0 is. If there's any kind of adjustment in phase or the amplitude, which happens in wireless with multipath or other types of issues, that dot, the amplitude or phase, can be shifted a little bit. So if it's BPSK, very reliable, there are two different areas. If it's anywhere on that left side, it will get corrected, and there will be no errors, no retransmissions. But if you look at 64 QAM, it's very lots of data, but not as good error correction. So if that same error happened if you're using 64 QAM, a higher modulation, there would be an error, and you'd have to retransmit. So this is why in wireless, when you're using higher data rates, sometimes you'll see errors, and you have to drop down to a lower data rate. Does that make sense?
The two axes, y, one of them is phase and others
Right.
look like what you have.
I've never seen that happen before. I wish that I had a beer. Well, okay, so here's an example that shows a real life case. Uh, so this is using 16 QAM. So with the different modulations, the higher the modulation, the more area you have, more dots you have, so more data. These are all different streams. So in this case, there are 16. It's better than BPSK, two different dots, but better error correction than 64 QAM, lower data. So in this case, it shows how an error happens. In wireless, we have an issue called EVM, error vector magnitude, and this happens in multiple situations. But the main could be if your transmit power is too high, sometimes radio quality is low. And this is a problem we see a lot in the lab. So as an equipment manufacturer, we have to deal with this on a day-to-day basis. Every radio that we ship, we have to test for this before it gets shipped to customers. So we actually transmit at different modulations and measure the EVM before shipping to customers. So I included this slide just as an example of what it looks like if you measured the phase and amplitude of radios. This is actually the quality of it. And we took screenshots of our vector spectrum analyzer, or vector signal analyzer, and this is what it looks like. So the one on the left you can see is 64 QAM, just like the examples I just showed, but it's very clean. The dots are very tight. The phase and amplitude translate directly to this. It's a very good quality signal. But on this side, this could happen for multiple reasons, multipath or poor quality radio or anything like that. You can see the dots spread out more, so there are a lot of errors that could be happening. So this is what it would look like if you translate from the radio waves to the binary data that you get. It goes from the radio waves to that, and then the radio can look at this and translate into the actual data. Any questions? Ready for the test? Okay, next section. I wanted to add some slides about antennas because we deal mostly with outdoor wireless. With outdoor wireless, you need big antennas, high gain directive antennas to point to the other side. Indoor, with indoor access points, the ones you have at your house or your office, it's more omnidirectional. So you just plug it in. You don't have to worry about pointing it. It emits RF in all directions. That's what we call omnidirectional. Let's see, I'm going out of order. Let me fast forward. So omnidirectional is kind of like a light bulb, right? It transmits RF in all directions. With high power wireless or outdoor wireless, we use more directive antennas. So a dish or a sector or panel antenna, and these are more like a laser beam. So if you were able to see the RF emitted from that antenna, it would look like a laser beam. And the main way we measure this antenna power or the beam is by gain. Gain is the way to measure the directivity of that antenna. Usually the higher the gain, the higher the quality of the radio link or signal that you'll have. So in most cases, we recommend you should try to get as high a gain of an antenna as you can. Now the downside of that is, uh-oh. I think there's some animations. Sorry about that. So the downside of gain is size. To get a higher gain, you'll need larger antennas. So if you ever see antennas on roofs or buildings and they're really big, that's why they're so big. Is the small antennas have small gain, they're not as directive. So gain really makes up the directivity. So the more focused or directive, like a laser beam it is, the higher the gain. But in order to do that, you need really big antennas. So usually you have to decide, do you want something that looks nice, small antenna, but not as directive, or big antenna, better performance? And another thing I wanted to mention is this also depends on frequency. So the lower the frequency, like 800 megahertz, 900 megahertz, you'll have really big antennas because it's directly proportional to the wavelength of the antenna, like I mentioned earlier. So 900 megahertz antennas are really big. And then you get to 2.4 and 5 gigahertz, and those antennas, for the same amount of gain or directivity, they're a lot smaller. And then it gets even smaller with the ones like 24 gigahertz, the 24 gigahertz link that you guys installed this week. They're pretty high gain, but they're pretty small compared to the smaller frequencies. And then the next slide, last thing I wanted to talk about for antennas is polarity. So radio waves, they travel just like it is shown in the video. The wave travels like this, pretty self-explanatory. But these are called polarities. So one radio can be transmitting like this polarity, which we call vertical polarity, and then another radio can travel on a different polarity, horizontal or diagonal, it doesn't matter. So what's cool about this is they don't interfere with each other. Vertical polarity, horizontal polarity, they don't interfere. So we can take advantage of this, and a lot of products now use what you've heard of a MIMO, multi-in, multi-out. They take advantage of cross-polarization and use multiple polarities to kind of use the same amount of spectrum, same frequency, so you're not wasting any spectrum, and kind of add those up to create additional performance. So we've seen some radios now using 8 by 8. And indoors, the way that works is one of the antennas transmits, it bounces off the wall, and another antenna receives it and uses multipath to create these different polarities and kind of mix them all together. So it's pretty cool. Any questions on antennas?
If you not just only use vertical and horizontal polarization, but all the angles between, you could get up to 360 or infinite different signals. Is there any border until you can spread this polarization
Right.
usage?
Theoretically, yes. And we tried to do this. But there's an issue with wireless and polarization. When you transmit, there's what's called cross-polarization discrimination. So the polarization can actually shift a little bit. And I think it's maybe 20, 30 degrees, something like this. So if you transmit on vertical and you have something else that's maybe 10 degrees off, it still may interfere with each other. So what we've been successful with is two. One vertical, one horizontal. It's been pretty good. We've tried others, but haven't been successful so far. Okay. That went quicker than I thought. Anyways, next thing I wanted to talk about, like he alluded to, Ubiquity. Like I said, we manufacture technology equipment. We do outdoor wireless, indoor wireless, routers, switches, IP cameras. We sell to customers all over the world. We've shipped over 20 million devices. We're also getting into cloud software and hosted solutions and things like that. So one thing that we'd like to really start doing is taking security a lot more seriously. And this is one of the reasons that I was interested. Up this to all of you guys or our community, our customers. And if you have any kind of vulnerabilities that you find, we'll give rewards. So of course, cash rewards, public recognition. We'll have a leaderboard on our site and things like that. We haven't officially launched it yet. We're rebranding our website now. We'll have a new website launched this month, and it has a section dedicated to this. But for now, if you have any questions or any vulnerabilities that you already know about, you can send an email to security@ubnt.com. and we'll work with you. That's Momo already sent one. I think that was actually our first official CVE issued. So.
If I may comment on this, I was, as Matt told me this, I think 2 days ago, no, 1 day ago, I was really amazed that Ubiquiti actually did something and thought about implementing a process for handling security vulnerabilities. Because as I contacted them, I was in first level support, had to deal with people who have no idea what was either PGP or CVE or whatever, and now they have a process for it. It's pretty cool.
Yeah, I mean, from our side, we've had some pretty major issues in the past that caused us a lot of problems. The worst one was, I don't know if you guys are familiar with our products too much, but we had an issue called Skynet that took someone emailed us maybe 2 years ago, and the email got lost, and we didn't know about it. But these guys said, well, screw you guys, we're going to create a worm, and they created this worm that exploited some vulnerability in our web service on our products, and tens of thousands of devices had their bootloaders erased. It wasn't good. So things like this, we don't want, we don't want. So we're willing to work with the community if things like that happen. So and that's it. So if you have any questions, comments, suggestions.
If you enter into Google Heise and Airfiber, then you see a text from them, from Heise. It's a big news site for here, and you can see that you can't use the Airfiber in Germany because it sends too high level data, too much dB and power. Yes. Can you say something about this?
Specifically about Germany, I'm not sure. We have a compliance team. They could tell you. Maybe you guys probably know more.
As we have set up an Airfiber link.
Don't tell anyone?
Exactly, don't tell anyone, no. In Germany, there is the 24 gigahertz band is mainly used for car radar, which is car auto brake systems. If the car gets too close to another car, they start braking. And what you have to do in Germany is you have to have neither excess 23 dB, I'm not sure, nor place the air fiber in an angle other than 90 degrees to the ground. If you do so, and I've tried this with my Mercedes, if you point the air fiber to a Mercedes which is quite new, it will start beeping as it thinks it's colliding with a car. Don't tell anyone I did this.
Cool. I'll have to try this.
Any further questions? More?
I have some talk to the Bundesnetzagentur about your products, and we've first had to search very intensive for your declaration of conformity, and now we found it, and there is something about everything is okay, but if you look in your documents, you see that you can that the dB you enter in your products is the dB before your antenna, and if you have a gain in the antenna, then it wouldn't be enough. Can you tell me now if it is in the ranges? Means if I enter in the GUI 23 dB, it is without antenna or with, or is it really a problem in Germany?
I really don't know. I'd have to ask our compliance experts.
Okay.
It's like I said, it's really hard. We have so many countries, and they're all different, so it's hard to keep track of everything. So we have people that's their full job is to keep track of different countries and the rules.
Matt, do you have an email we can send to you?
Yeah. My email is matt@ubnt.com. It's okay. Can you read this? No? I guess I should use this. Matt at UBNT. Don't try to hack into my email. So any questions about, go ahead. Change my password.
Hi. I have one question regarding one of your previous slides. How does the waveform map to the different points in the constellation graph?
Okay, I'll use the whiteboard. Let's see. So I'll do something very simple. This may not be exactly correct, but you'll still get the idea. So the wave looks like this, right? If we change the amplitude, let's say with 64 QAM, there are 8 different possibilities for amplitude. So it could be like this, or it could be like this, or like this, something like this. So the amplitude could look like this. Make sense? At the same time, we can change the phase. So like I said, shifted. So it could look like this. So instead of going down where it normally would, it would be shifted over a little bit. And then the same here, instead of going back up, shift it over like this. So there are 8 possibilities for phase as well. And you multiply those together, and you get this constellation. So let's see. Just imagine a lot of dots, right? So I don't know exactly which one matched to which, but let's say this one moves, the amplitude is a little bit lower, and then it gets shifted. Maybe it matches over here, that one. But if this amplitude shows up a little bit higher, the dot could appear maybe right there, something like that. So these map directly to one of those items. And that's how it translates from the actual waveform into the binary data that is decoded. Does that make sense?
Actually, it helps if you remember how you learned about sinus and cosinus in the school. There we had this circle where we had one dot, and then we turn the circle around, and we map that to one dimension. Then you get a sinus. So these dots, that's the point at the circle that you turn around. That's the 0 point where you start your sinus. So if you have a bigger amplitude, then you're far out to the top or to the left right, there you have a big amplitude. If you shift your sinus, then you turn around your circle a little bit, and you get some other starting point of your turning around your circle. So everybody who still remembers this will have an idea now what we see there, where the dots are. And who not, well, we can remember, you can just try to accept that we have, the phase is just something that goes around on the middle, and the amplitude is the what's Abstand in German, I don't know, the distance from the center point.
Do we have any more questions? One more?
Will the slice be online somewhere?
Good question. I can share something. Oh man.
We'll make that happen, Matt.
Any thoughts on the security program? Who's going to be the first? Any of you going to find anything? Maybe we'll give a reward for the first person.
I'll have.
You don't count.
I'll find more.
Okay, well, thanks for having me. It was fun coming. Also, Edmundus is here with me. He's from Lithuania on our AeroS team. Thanks for having us, and if you have any questions, just stop us and chat.
I heard Matt really likes Club Mate, so if you have any questions or want free RF theory class, I think Matt is available for Mate.